AI can now give you an answer in seconds, but your business may still need days, weeks, or months to find out whether that answer actually worked. And that gap is going to matter a lot. Imagine a manufacturer running a high-value production line. The line makes specialty material. Defects are expensive. Rework is expensive. And client complaints are worse. So the company feeds years of production data into an AI system. Sensor readings, supplier lots, maintenance logs, quality results, shift data, temperature ranges, and throughput targets. The AI comes back almost instantly. Change this process setting. Run a slightly different temperature range. Tighten this timing window. And increase throughput here. The recommendation looks precise. It looks confident. And it may even be right. But the business does not learn that in seconds. The line has to run. The material has to cure. Quality has to inspect it. Maintenance effects may show up later. A supplier issue may appear only after several batches, and the client issue may not show up until the product is already downstream. That is the point of this piece. AI is making answers cheap, but learning is still expensive. And the companies that win with AI will be the ones that make learning cheaper too. Hi, my name is Vlad Stoyanovsky, and this is the Sovereign AI Enterprise, where I look at what happens when AI moves from impressive demos into real enterprise operations. Today's topic is simple. AI is making answers cheap, but learning whether those answers actually work is still expensive. I'm recording this outside on a hot summer day, surrounded by trees, which is actually a useful reminder. You can look at a tree and make a quick prediction about whether it will survive the heat. But the proof comes later. Did the roots have enough water? Did the leaves recover? And did the stress show up next month? The real world answers slowly, and enterprise AI has the same problem. This first visual shows the gap. AI prediction speed is rising fast. The enterprise abilities to test, measure, and learn is moving much more slowly. That gap is where a lot of AI value gets trapped. The cleanest warning comes from pharma. Since roughly 1950, the number of new drugs approved per $1 billion of research and development spending has fallen by about half every 9 years. Adjusted for inflation, that is often described as an almost 80-fold decline in research productivity. The industry gave that pattern a brutal name: Eroom's law. Moore's law spelled backward. The name works because the contrast is so stark. In computing, scale made the core unit cheaper, faster, and more powerful. In drug discovery, better instruments, larger dataset, computational biology, automation, and management discipline did not produce the same curve. The cost of proving what works kept rising. That makes Eroom's law more than a pharma story. It points to a broader enterprise problem. Recommendations are getting cheaper, but proof is still expensive. And you can see the same pattern in manufacturing, logistics, banking, insurance, utilities, procurement, and IT operations. AI can suggest a route, a price, a maintenance plan, a supplier substitution, a credit exception, or a claims pathway almost instantly. But the expensive part is what happens next. Did the route actually save money after congestion, customs delays, fuel costs, and client impact? Did the supplier substitution hold up under quality review? Did the faster claims pathway reduce handling time while increasing leakage, complaints, or litigation? And did the AI recommendation improve the real system, or did it just improve the dashboard for a few hours? That is a distinction leaders need to get sharper about. Prediction is the cheaper part now. Let's get back to the manufacturer. For the production team, the AI recommendation feels like the breakthrough. And in one sense, it is. The team no longer starts from a blank page. The AI can scan years of batch data, compare machine settings, read maintenance history, correlate supplier lots and quality outcomes, and flag patterns that would take engineers weeks to reconstruct manually. That is real progress. It changes the speed of analysis. But it is still the front end of the loop. A recommendation is a claim about what might work, but it is not evidence that the business has learned. The AI can identify the likely defect driver, the likely supplier issue, the likely route problem, and the likely credit risk. But the enterprise still has to act, observe the result, and decide whether the recommendation improved the real system. Many companies are treating faster recommendations as faster learning. That is the trap. AI can reduce the cost of forming a hypothesis, but the enterprise still has to prove whether the hypothesis improved the business. Now, suppose the manufacturer accepts one recommendation. The AI suggests a small process change on a high-value line. Nothing dramatic. A slightly different temperature range, a tighter timing window, and a throughput target that looks achievable based on prior runs. The recommendation is backed by historical data, and it fits what the production team already suspects. The line is capable of more than it is producing. The first shift looks good. Output improves, the dashboard moves in the right direction, and the recommendation appears to have worked. But then the second order effects start to show. Scrap rises on one product variant. A quality inspection catches a surface inconsistency that was not visible in the first yield report. Maintenance sees early signs of stress on a component that usually lasts longer. The production team realizes the setting works better with one supplier lot than another. And a downstream client reports variation that did not appear in the standard plant metrics. This is the moment the clean AI answer meets the operating system of the business. The setting changed quickly, but the evidence arrived across production, maintenance, quality, supplier behavior, and the client experience. The AI was not simply wrong. That would have made the lesson easier. It just optimized against the data it could see. But the operations contained variables the recommendation did not fully price in. Material variation, machine wear, inspection lag, shift behavior, supplier inconsistency, client tolerance, and the difference between a clean metric and a usable product. Real systems do not answer cleanly. They answer through delays, exceptions, side effects, and partial signals. That is why reality is the hidden second half of the AI system. Until the enterprise can connect the recommendation to the operational result, it has improved the speed of advice, but it has not changed the learning cycle. The manufacturer's problem is easier to understand in the place where the loop is most explicit: the lab. Self-driving labs started in experimental domains like chemistry, material science, and drug discovery. They're often described as robot chemists. But the useful idea I want to discuss is the loop, a system that can form a hypothesis, run an experiment, measure the result, learn from the outcome, and choose the next experiment. That is different from ordinary automation. A conventional automated system runs on a predefined process faster, but a self-driving lab changes the next experiment based on what the last one revealed. It reduces the time between idea evidence, and adjustment. That is the lesson for the materials manufacturer. The plant does not need to become a lab in the literal sense. It needs to copy the useful part. Treat the AI recommendation as the start of a controlled test, measure what happens, and use the result to improve the next decision. This is the pattern: hypothesis, experiment, measurement, failure capture, and next decision. The breakthrough is the shortened path from idea to evidence. Every industry has its own version of the lab. In manufacturing, the lab may be a production line. In logistics, it may be a route network. In insurance, it may be a claims operation. In IT, it may be an estate of infrastructure, incidents, remediation actions, and post-change validation. Here, standing outside in the summer heat, the analogy is pretty simple. If you change how you water these trees, the recommendation is not proven when you turn on the sprinkler. It is proven when you see what happens later: which leaves recover, which branches stress, which soil holds moisture, and whether the next watering decision gets smarter. That is what enterprise AI needs: a shorter path from recommendation to evidence. The manufacturer may want to look back at previous attempts to improve the same line, but the useful evidence is everywhere and nowhere. One engineer remembers that a similar temperature change caused problems last year. A maintenance ticket mentions unusual wear after a prior throughput push. A quality report shows a defect pattern that appeared for only one product variant. Procurement has notes on a supplier lot that behave differently from the others. And a shift supervisor remembers that the setting worked better at night when the line ran with a different crew and fewer changeovers. All of this is valuable, and most of it is exactly the kind of evidence the next recommendation needs. But the business did not preserve it as learning data. It preserved it as fragments: ticket comments, meeting notes, dashboard anomalies, email threads, local memory, and after-action explanations. Successful changes made their way into the process, but failed attempts stayed behind as ticket comments, meeting notes, and things experienced operators remembered. Most companies are better at recording transactions than experiments. They know what was ordered, approved, shipped, paid, closed, repaired, or escalated. They are less disciplined about preserving what was tried, what was rejected, what almost worked, what failed under specific conditions, and what an experienced operator overrode before it became visible in the metrics. This is important because AI trained only on completed transactions and approved decisions sees a cleaned up version of the business. It sees what survived the process, but it does not see enough of the rough terrain around it. It may know the final supplier, but not the rejected substitute that failed quality review. It may know the approved maintenance plan, but not the workaround that prevented a larger outage. And it may know the successful production setting, but not the boundary conditions that made nearby settings fail. Failure data is not operational debris. It is the map of the terrain. A company that cannot remember its failed experiments will keep asking AI to make recommendations inside a partial picture of reality. So the practical question is, where does the business learn too slowly? For the manufacturer, this is not abstract. The team is constantly adjusting the line. If the setting is wrong, the cost shows up in scrap, rework, downtime, warranty exposure, and client complaints. The problem is that the evidence arrives in pieces. Yield shows up quickly, but machine stress takes longer. Supplier variation may take several batches to see. Client impact may not show up until the product is already downstream. That is a loop worth improving. Across the enterprise, the best candidates are repeated decisions with measurable consequences. Pricing changes, maintenance deferrals, supplier substitutions, logistics reroutes, credit exceptions, claims pathways, and production settings. Here's the practical inspection. Ask 5 questions. 1. Where do we make repeated decisions under uncertainty? 2. Where does the outcome arrive late, indirectly, or in another system? 3. Where do failed attempts, operator overrides, and near misses disappear? 4. Where can we test a recommendation on a smaller slice before scaling it? 5. Where would faster learning improve margin, uptime, quality, safety, capital efficiency, or client experience? That last question is key because not every loop deserves the same attention. Not every use case is worth building around. Some decisions do not happen often enough. Some outcomes are too hard to measure. Some changes take too long to evaluate. And some AI ideas sound interesting, but they do not move anything important in the business. The best loops have a few things in common. The decision happens again and again. Getting it wrong is expensive. The result can be measured, and the business can compare one option against another without redesigning the whole operating model. That is where AI has something concrete to improve. The best AI use case may be the loop where the company is already paying too much to learn too slowly. So the manufacturer does not need to redesign the whole plant. It starts with one repeated decision on one production line. Which process setting to use for a specific product family. That is narrow enough to manage and important enough to matter. The first build is a simple learning loop. Here's the loop. Define the decision. In this case, the decision is the process setting the AI recommends before the run. Define the action. The action is the controlled change made on the line. Machine shift, batch window, product variant, supplier lot, and operating conditions. Define the outcome. The outcome is not one metric. It includes yield, scrap, rework, inspection results, machine stress, maintenance notes, and downstream quality signals. Capture the exceptions. Record when operators override the recommendation, when the setting is rejected, when the result is mixed, and when the apparent win creates a later problem. Compare alternatives. Don't just ask whether the AI recommendation worked. Ask where it worked, under which conditions, compared with what previous setting, and at what downstream cost. And feed the result forward. The next recommendation should be shaped by the prior result, including failed attempts and boundary conditions. The first implementation step is to make every recommendation leave a usable record. Each recommendation needs a trace. What the system recommended, what evidence it used, who approved the test, where the change was applied, which conditions were present, what outcome followed, which exceptions appeared, and what changed for the next decision. The evidence will usually sit across production systems, quality reports, maintenance tickets, supplier records, operator notes, and downstream client issues. The work is to connect these signals around the decision. Without that record, the company is only running faster recommendations. It is not building memory. That same pattern applies outside manufacturing. Pick one decision that repeats, costs money when wrong, and produces observable outcomes. Start with one loop where better feedback can change the next decision. The useful metric is learning cycle time. How long it takes to move from recommendation to action to observed result and to a better next decision. That is where leaders should begin. Make one loop learn faster. The manufacturer does not win because the model generates more recommendations. It wins when each recommendation makes the next one better. The process setting is tested, the result is measured, the exception is captured, the failed condition is preserved, and the next decision carries more evidence than the last one. That is the practical lesson behind Eroom's law. Pharma gave the pattern a name because its productivity crisis was impossible to ignore. Other industries may not call it Eroom's law, but many live with their own version. Rising cost, slow implementation, fragmented feedback, and wasted failure data. AI will keep making prediction cheaper, and that is important. But prediction is only the start of the operating cycle. The bigger advantage belongs to companies that reduce the cost of learning from the real world. So when leaders ask where AI should go next, I would start with a different question. Where is the business already paying too much to learn too slowly? Find that loop and make it visible. Connect the recommendation to the action. Connect the action to the result. Preserve the exception and feed the evidence into the next decision. AI will make answers cheaper, but companies that win will make learning cheaper too.
The data flows, a constant stream, shaping futures, chasing every dream. Complex patterns and sights unseen, a new era, sharp and keen. The world is changing, can you feel the pulse? A deeper vision beyond every impulse. Enterprise, geopolitics, AI.